All right, so what we have here is going to be another rotational kinetic energy problem. So I've got a mass attached to a string which is wrapped around a flywheel. So a flywheel, think of it's like a big, massive wheel. Think about this almost like a yo-yo, an upside down yo-yo. You're holding here. This is fixed to an axle, and the string's gonna unspool and the flywheel is gonna stay in place and spin. Right. So in this case, is my center of mass moving? My center of mass isn't moving. It's fixed in place. It's on an axle. So I'm not going to have linear kinetic energy. I'm just going to have rotational kinetic energy. So the question we're going to want to know is how fast will this mass be moving after it falls some distance? Let's say after it falls, I don't know, let's just pick 2 meters again. So how fast will the mass be moving after it falls 2 meters? Now this problem could be done with torque, and you could find angular acceleration. You can turn that angular acceleration into speed. That's a lot of work. Like we really should do this with energy. Just like actually the half Attwood machine is much easier done with energy, much more easily done with energy. So we need to mark on here our radius just so we know what we're talking about. There's R. So as this guy spins, right, this guy falls down, this guy's going to spin, and I have to share that energy. So what's my initial energy going to be? Well, my initial energy is going to be my potential energy plus my kinetic energy. But I know that my initial kinetic energy is 0 because we're releasing it from rest, right? So I'm only going to have potential energy. So my initial potential energy is going to be mgh, and we said h is 2 meters. So let's put that, so 2 meters, right? So now my final energy, of course, is going to be U final plus kinetic final. But this is going to be 0 because it's fallen as far as we're allowing it to fall, so I don't care about that anymore. And my final kinetic energy is going to be, well, okay, so this guy just has rotational kinetic, right? But this guy's got linear. So I have to track both. So I have to say 1/2 mv squared, so note the difference between big M and little m, plus 1/2 I omega squared, right? And so what is I in this case? Well, this is a cylinder again, so we have the moment of inertia for a cylinder is 1/2. So it's going to be 1/2 big M r squared, right? So now I'm going to do the same thing I did in the previous problem. I'm going to take this potential energy and set it equal to this final term, because I know that my initial energy all is going to go to my final unless there's friction or some other way to lose energy. So I can do E naught equals EF, right? I mean, very standard stuff. So I'm going to get mgh is equal to 1/2 mv squared plus 1/2 I omega squared. But now let's replace the things in this term. So we have, just rewrite the rest of this equation. 1/2 mv squared plus 1/2. Now I, we said, was 1/2 big M r squared. So let's put that in parentheses. Keep track of that. And then omega, as always, we've done omega before. We know that omega is equal to V over R. And we want to put it in terms of V, because it's more standard, it's a little bit easier to work with for us. So let's slide this paper up. Okay. So now I can replace this with V over R squared. And just like before, hey, this R and that R cancel, right? But now my masses don't, because this is a different mass. This is little m, that's big M. So it can't quite get rid of the masses here, because the mass of this flywheel is going to matter. Okay, so I still have to solve for V. So now I'm going to have mgh is equal to 1/2 m v squared plus 1/4 big M v squared. And those are the same v because when my flywheel's turning, this is all wrapped around by this string, right? This string is going around the whole thing. So the outer edge of the flywheel has to be moving at the same speed the string is, and the string has to be moving at the same speed the block is, right? So those are going to be the same. So now we're solving for v, so let's go ahead and factor out my v's on this side. So I'm going to get 1/2 m plus 1/4 big M v squared is equal to mgh. So now I've got v here where I can divide both sides by this term, and then I'm going to get v squared alone. So I'm going to get mgh over, we can multiply through by 4 also if we want to make it easier. So let's go put a 4 up here. So now it's going to be 2m and big M. 2m plus big M is equal to v squared, right? So this means then that v is going to equal the square root of 4mgh over 2m plus big M, right? So let's put some numbers in. Let's come over here. We've got a little more space. So this is going to equal to the square root of, we said little m was 2, so 4 times 2, and g is we're going to use 10, and h we said was 2 also, I believe. Yes, we did. Times 2 divided by 2 times, well, little m is 2, and big M is 5. And once, oh, you guys didn't see a lot of that. I'm going to slide that up so you guys can see. So now we're in calculator territory again. Let me get that out. Next time I'll try to remember to pause the recording when I get the calculator out. Make things go a little bit smoother. So, clear the number from the last one. I want to do 4 times 2 times 10 times 2. Give me 160 on the top. And then let's divide that by, do I not have parentheses in this mode? Let's turn this sideways so we get a nice scientific mode. So we can use our parentheses. Divide this by 2. Let's put a parentheses here. Times 2 plus 5. Now let's close our parentheses and get our 9, which we could have done that in our head, but so we get 160 over 9 is 177.8, and then we'll push the square root button, and so our final answer here is going to be that v is equal to 4.22 meters per second. All right, and that's going to be it for this one, guys. I will see you in the next video.